Dear colleagues, we're almost ready to start our evening plenary session. And today we have three presentations, all from the United States of America. And I suggest that we start with the first one with Professor Ken Golden from of Utah. Great, nice to see you here. If I'm not mistaken, the weather in Utah is almost like here in St. Petersburg, something 30 plus.
Yeah, I saw that actually, except last week in Salt Lake City, it was 42 Celsius. We hit a record, yeah. But you seem to be having very similar weather, especially for St. Petersburg.
Yeah, and the humidity here is awful, so that's a challenge. But after these three presentations, those who are offline would be happy in joining welcome party, and those who are online could join their own welcome parties at home or in the office. So it's exactly 5:15 Moscow time. Professor Golden, the floor is yours.
Okay, thank you. Let me go ahead and share my screen with you. Please let me know if it, just to make sure it looks okay. There we go. Can you see that? And my let's see there, and my cursor?
Yeah.
Perfect. Okay, then I'll go to let's see, to full screen. There. Very good. Okay, well, I wanted to thank the organizing committee. It's certainly a pleasure to be able to share this with you today. I do certainly wish I could be in St. Petersburg. I've been really looking forward to getting back there. I've been there many times, but here we are still in the situation that we're all in. Hopefully soon, maybe next year or something, we'll be able to join each other in person. So I'd like to tell you about work that we've been doing for many years on studying sea ice and particularly its role in the climate system. But what I think is interesting for this particular community at this conference is that many of the issues that we encounter in modeling sea ice seem to overlap with many of the topics of interest that come up at this conference. So already here, this is actually a photo from Antarctica, but it's in the springtime. You see, in fact, thinning sea ice, and I'm going to tell you about our work on modeling sea ice, and of course, its role in the climate system. So why study sea ice? Well, there's still a lot of it. It's reducing, but it covers about 12% of the Earth's ocean surface. It forms the thin frozen boundary layer between the ocean and the atmosphere in the polar regions. And as such, it mediates the exchange of heat, gases, and momentum. Here you see heat rising up through a lead created by the motion of this icebreaker in Antarctica. Both the freezing and the melting of sea ice play a major role in global ocean circulation. And as you'll see, sea ice hosts a very rich ecosystem in the polar oceans. And as this very thin frozen boundary layer, sea ice is a sensitive indicator of our warming climate. One of the main jobs that the polar sea ice caps play and accomplishes is in reflecting incoming solar radiation during the polar summer, as you see here. So this is measured by what's called the albedo, the ratio of reflected sunlight to incident sunlight. And whereas white polar ice caps reflect most of that incoming solar radiation, if you lose that white icy surface, and in particular, if it's replaced by a darker absorptive surface like the ocean, then you're going to continue to absorb more heat, warm the ocean, and even melt more ice. This is what's referred to as ice albedo feedback. And this is one of the main mechanisms that's driving the precipitous losses that we've seen, particularly in the Arctic. And here you see sort of a median extent of sea ice at its minimum in September. But here's where we were just last September, and you see how much we've lost. In fact, we've lost on the order about half of the summer Arctic ice pack, which we saw much of the earlier part of the satellite era. One of the interesting features here is this hole in the data. This is called the polar data gap. And one of the things I'll talk about is how we're using some interesting mathematics to try to fill in that data gap and figure out what kind of sea ice concentration we're looking at around the North Pole. Because it used to be assumed that it was just all ice, but with global warming, that's not the case anymore. Now, predicting sort of what may come next after we've had these precipitous declines, do we recover? Do we stabilize? Or most likely, do we see ice-free summers sometime in the next 20, 30, 40 years? This requires a lot of math modeling, and that's really what we're engaged in. And one of the extremely important features of sea ice that drives much of the type of modeling that has to be done is the fact that sea ice is a complex, multi-scale composite material that exhibits interesting and fascinating structure over length scales ranging over about 10 orders of magnitude. So these are the sub-millimeter scale brine inclusions of sea ice, which actually they can coalesce to form these very large structured brine channels through which fluid can flow. Of course, you're freezing something, so in fact, it's a polycrystalline material. And in fact, the exact polycrystalline structure depends upon what type of formation conditions you have when the ice freezes. Now moving up in scale to this mesoscale, then you have Arctic melt ponds that have, say, meter scale substructure and pressure ridges. And then when you look from space at the ice pack, you see a granular medium, which I know is actually a topic of interest that I've seen at earlier APM conferences. Okay, now one of the main issues that we have to deal with when you're dealing with a composite is what's the effective behavior? You have complex microstructure, and then the question is what's the behavior on the large scale? Now, say here we have, say, a two-phase composite, good conductors, say in an insulating host like brine in ice. And then as we step back and look on the macro scale, what we want to know that what is the effective conductivity or the homogenized conductivity? This is the so-called forward problem. And then if we make measurements of the bulk behavior of a composite, the inverse problem consists of trying to figure out or invert for the microscale information. What's the volume fraction of the inclusions? And this homogenization problem has a long and storied history, going back to scientists such as Maxwell and even Einstein. And there was a lot of progress in the 20th century. And in fact, the widespread use of composite materials in the late 20th century was due in large part to making significant advances beyond sort of trial and error in the laboratory, but to be able to mathematically predict what the effective properties of complex composite materials are. So in a nutshell, what's this talk about? How we're using methods of homogenization and statistical physics to model sea ice effective properties and ultimately advance how sea ice is being represented in climate models and process studies and so on. And so we'll take a tour of critical sea ice processes on the micro scale, on the mesoscale, and the macro scale. But what I think should be particularly interesting to this audience here is from our mathematical approach, we don't care where we get the ingredients to our theories. In other words, if the math fits, let's use it. So we have lots of different kinds of ingredients, theories of composite materials, stealth technology and electrical engineering, porous media, oil extraction, the mathematics of carbon sequestration, statistical mechanics of ferromagnets, Anderson localization and semiconductor physics, phase transitions in percolation theory, random matrix theory, differential equations, and so on. There's many, many different kinds of mathematical and theoretical physics techniques that we use, that we bring to bear to study sea ice. And then, similarly, our work on sea ice, we prove general theorems and develop models about the behavior of sea ice. And however, there's lots of impact and implications of our work because we're proving general mathematical results often. So our work impacts sea ice physics and biology, theories of composite materials and polycrystalline materials, remote sensing, advection diffusion processes, biomedical imaging, biomaterials, and also we have an emerging group and strength now in the microbes, the ecology of the microbes that live in sea ice. Okay, so how do these scales interact? Well, starting at the finest scale, the sub-millimeter scale brine inclusions, they impact the fluid permeability of the sea ice, how easy it is for fluid to flow up and down. But then the meter scale topography of the snow, that sort of gives the geometry of these melt ponds that are on the surface of when sea ice melts in the spring. But then on much larger scale, you're interested in what's the overall albedo or reflectance of the ice pack, and then upscaling to the global scale. Okay, so let's focus on the microscale first. Well, as I mentioned, fluid flowing through this porous microstructure of sea ice governs key processes in polar climate and ecosystems, such as the evolution of these melt ponds. Whether or not they grow or drain overnight is completely determined by how easy it is for fluid to flow through the porous microstructure. As I said, there are robust algal communities that live inside the fluid inclusions of sea ice, and they get their nutrients through nutrient-laden seawater percolating up through this porous microstructure. Now, one of the key structural features of sea ice is effectively something that we discovered out in the middle of a storm in Antarctica in 1994, which, roughly speaking, we can think of as the on-off switch for fluid flow. So we're talking about the data on the vertical fluid permeability of sea ice as defined by Darcy's law, where the fluid permeability tensor is a homogenized parameter. And so roughly speaking, for classic congelation-grown columnar sea ice, for brine volume fractions below about 5%, the sea ice is effectively impermeable to fluid flow. However, for brine volume fractions above 5% in columnar ice, the sea ice is permeable, and increasingly so with increasing brine volume fraction or temperature. And this critical brine volume fraction of 5% corresponds to a critical temperature of -5 Celsius for a typical bulk salinity of 5 parts per thousand. Hence, this has become known as the rule of fives. And it sort of really determines what goes on from so many of these key physical and biological processes in sea ice. Now, it turns out that essentially what's happening, this on-off switch, is determined by the conductivity of the brine phase, which we realized is being controlled by what's called a percolation threshold in percolation theory, which was originally developed for studying sandstones in the late 1950s. So you start with a 2D lattice, a 2D square lattice. Bonds are open with probability P, closed with probability 1 minus P. And so the dark bonds here are where fluid or electricity can flow. If only 1/3 of them are filled, then fluid or electricity can get a little way through, but it can't get through the entire lattice, which we assume to be infinite. However, here 2/3 of them are filled, and so and there does exist an infinite cluster, a cluster of open bonds, or a pathway through which fluid or electricity can flow. But then the real question is, what is the percolation threshold, the smallest value of P for which there's an infinite open cluster? And for the two-dimensional square lattice, it's known that it's exactly 1/2 or 50%. So why in the world are we down so far at 5% for sea ice? And it turns out that there's an excluded volume effect, that the brine inclusions, the fluid phase in sea ice, is not just randomly distributed, it lives on the boundaries between the individual crystals. And it turns out that it's extremely similar to the microstructure of so-called compressed powders, big polymer spheres and little conducting particles that are then squashed to form these so-called compressed powder microstructures. But if these particles are highly conducting, then this is what is known as a radar-absorbing composite that was used in the development of stealthy aircraft to evade radar. And so we employed this continuum percolation theory that gives the percolation threshold for these kinds of materials, and we applied it to sea ice, and we're then able to predict the 5% and all kinds of data on ice production and algal growth and so on. And as a consequence, sea ice itself is a radar-absorbing composite, which means that one of the very difficult questions in climate change research is what's the thickness of sea ice? How do you get your hands on how thick the ice is? It's a difficult problem in remote sensing and the interaction of electromagnetic waves with sea ice. All right, the next big step was to get a theory for how the permeability of the sea ice depends on the temperature. And as also to confirm our rule of fives, because we didn't really have any direct evidence of that there was a real percolation threshold in the brine microstructure. But we developed an X-ray tomography method, which finally demonstrates this. It took a long time, but we finally did this. And then also we developed a beautiful multifaceted theory of the fluid permeability in sea ice. Here's the 5%. There's the best known value for the critical exponent that describes the takeoff of the permeability. And then here's a factor in front, which is interesting. This is not a fudge factor that we fit to the data. It's actually something that we predict from our X-ray tomography and a very interesting theory called critical path analysis that says for fluid flow or electrical flow, bottlenecks control the flow. And what's interesting, which I should mention here, this work with Sergei Kozlov, a mathematician who worked at the Moscow Civil Engineering Institute back in the 1980s and 90s. He was a very good friend of mine, and I went to visit him for a summer in Moscow in August of 1991, which some of you may remember. And I landed in St. Petersburg and met, I think, the third speaker, Andrei Turkayev, and during that visit, and then I went to Moscow to work with Sergei on this, to develop this theory that we eventually used much later in sea ice research. But it was through that visit where I got to sort of experience what went on in Moscow that summer and go down to Red Square and see the tank. Anyway, it was absolutely fascinating. You knew you were witnessing history, certainly. And so this piece of work came out of that adventure, my first time into Russia. And okay, so this theory, though, works beautifully, I should say, and agrees very closely with field data. However, if there's algae in the sea ice, which we see all the time, they secrete what are called extracellular polymeric substances, which affect the evolution of the brine microstructure. And then we have to ask, well, how does the EPS then affect the fluid transport? This is sort of like algal goop that they use to protect themselves and to thrive, but it messes up the brine microstructure. And instead of a classic log normal, you get a bimodal log normal. Anyway, one of my PhD students did some beautiful work, getting rigorous theoretical bounds on the fluid permeability of sea ice, but also developing a numerical model to simulate what they were seeing in the field. Okay, this is a photo of me in doing the first measurements of fluid permeability in the Antarctic ice pack. And you might think, well, this is the notices of the American Mathematical Society. There's obviously a big experiment going on here, but in fact, they were out there playing soccer while all these experiments were going on. And let's see. Okay, so now this is going to set the tone for the rest, in some sense, the rest of the talk. And this is where a lot of the interesting mathematics comes in that extends to so many of these different types of problems. So we're going to approach this through the problem of remote sensing and the interaction of electromagnetic waves with sea ice and its microstructure. And ultimately, we're interested in measurements of the bulk electromagnetic properties and then recovering the brine volume fraction, information about the inclusions, the thickness, and so on. But it's going to introduce an important mathematical technique that turns out to be incredibly effective in a broad range of sea ice modeling problems. So we start with the quasi-static long wavelength approximation Maxwell equations, and then the effective complex permittivity is defined here through the macroscopic relation or average relation between the D and the E fields. And then the effective complex permittivity is a complicated function of the ratio of the local permittivities and the composite geometry. And then we're interested in what are the effective propagation characteristics of an EM wave, radar or microwaves through this medium. And the main method that has been extremely powerful and rigorous mathematics and beautiful theoretical physics, but also extends to all these other problems that I'm going to mention to you, And that's called the analytic continuation method, developed independently by David Bergman and Graham Milton. And then that was actually, Graham was an undergraduate at that point. And this was my first year of graduate school when we started developing with my PhD advisor, the underlying mathematics, which I'm going to say something I think you all will find interesting about. And so anyway, there's a so-called Stieltjes integral representation for this auxiliary function, which represents the effective complex permittivity. And what's so beautiful about this method is all the material parameters are contained in this complex variable, S, but all the mixture geometry, the information about the composite, is incorporated into what's called a spectral measure, the thing that you integrate against. And it's associated with a self-adjoint operator, gamma chi, where gamma is projection onto curl-free fields, gradient inverse Laplacian, where inverse Laplacian is, say, convolution with a Green's function. The randomness or the microstructure comes in through the characteristic function of the brine phase. And so the mass of this measure, say, is the volume fraction of the brine. The higher moments depend on endpoint correlation functions, but the key mathematical aspect which makes this problem go, as well as all these other problems that I'm going to mention to you, is this so-called resolvent representation of the solution to the problem, the electric field in this case. So this operator gamma chi, I think of as linking scales. It takes us from the micro scale rigorously mathematically to the macro scale. Now, this representation, this Stieltjes representation, it distills the complexities of mixture geometry into the spectrum, the eigenvalues and eigenvectors of an operator that plays the role of the Hamiltonian in physics. So the spectral properties of the Hamiltonian in quantum physics incorporate the subtleties and the interesting mathematical properties of the potential. And that's what we're seeing here. So one of the main ways that this framework can be used is to get rigorous bounds on effective properties, such as the effective complex permittivity, assuming various information about the microstructure, such as even the connectedness, how separated the inclusions are. So we have all sorts of interesting, rigorous results with my very close colleague, Elena Cherkayev, who's the real inverse expert. And anyway, so we can recover information about the brine volume fraction, the inclusion separations, and so on. So this very powerful method, it turns out that I wanted to tell you kind of where it all came from. Certainly it was the very beginning of my entire mathematical career came from this book that I'm showing you. It was by Akiezer and Glasman, Theory of Linear Operators in Hilbert Space. And you can see it was translated from the Russian. And this book this is what launched this whole mathematical theory of this analytic continuation theory and this resolvent structure. And it was their deep understanding of the underlying equations of mathematical physics, which allowed, and the way they formulate it, which from my perspective at least, allowed us to use this beautiful and sophisticated mathematical theory in all these other kind of problems, which I'm also going to mention to you as we go on. And another key theorem that gives these actual bounds, it's called the Krein-Milman theorem. And so, to be honest, this is one of the things I wanted to mention. I've never mentioned in a lecture before, but as I look back over my career, this is kind of what started my whole career. So my deepest gratitude goes to these early pioneers, and they were representative of the long history and tradition of this famous Russian school of functional analysis, basically what's known as infinite dimensional linear algebra. Okay, so one of the interesting spin-offs here is to relate sea ice to human bone and inverting for this spectral measure again. And this allowed us to establish a non-destructive way of monitoring the progress of osteoporosis, because of course the math doesn't care if it's sea ice or bone. Now, by developing a program where we can discretize images and so on of microstructures and then compute spectral measures, we found something very unexpected and fascinating. In other words, here's the ice pack, and we're looking at the area fraction of the ocean. And you see that it's opening up and finally percolating. We were able to calculate not only the spectral measure, but the eigenvalue spacing distributions. And we found something fascinating. They transition from completely uncorrelated Poisson distribution to where the eigenvalues repel each other. and they start to obey what's called the universal Wigner-Dyson distribution, and particularly the so-called Gaussian orthogonal ensemble. And it turns out that this is just a piece of a very rich picture, which is basically Anderson localization in wave physics, quantum, optics, acoustics, and water waves, where basically electronic eigenstates localize as you ramp up the disorder in the potential. And anyway, however, but that's all in wave physics. And what's one of the fascinating aspects of what we found here is that there's no wave interference or scattering effects. We see all the earmarks of Anderson transitions, the universal eigenvalue statistics, extended states, mobility edges, all the earmarks of quantum transport in solid state physics, but there's no wave interference. It's geometry driven. And we've extended this into a fantastic class of materials in quasi-periodic, spurred by the existence of so-called quasicrystals, and discovered that Sheckman got the Nobel Prize for in chemistry. And anyways, you take a moire pattern and just a small change in the so-called twist angle, and you go from purely periodic behavior to really random behavior with all the bells and whistles of Anderson localization, but within this class of deterministic quasi-periodic materials. Anyway, this is something new we found out one of my PhD students who's in physics, actually. Okay, we also study sea ice as a polycrystalline material, and where you have information about the distribution of the orientations of the individual crystals. And so we were able then to adapt this analytic continuation method, the Herglotz representation, the Stolz's representations, and so on, and the whole bounding theory, again, based on the framework that I just showed you, but to polycrystalline materials. And then ultimately, one of our goals here is to be able to develop rigorous inverse methods for distinguishing between columnar ice and granular ice. Why? Because they have such different fluid transport properties, which the biologists as well as climate scientists are very interested in. This very large difference that we discovered, and we have a new paper coming out and so on. Yes, okay. So on to just briefly on the mesoscale and the macro scale. So again, the robustness and power of this analytic continuation framework, now we've adapted it to the very interesting problem of ocean waves propagating through the sea ice pack. So now we view the sea ice pack as a two-phase composite material of ice flows and ocean. And one of my PhD students was able to, like a real tour de force of turning those mechanical equations to the analogs of the electromagnetic equations and develop a new Stolz's integral representation and the first rigorous bounds for the complex viscoelasticity of the sea ice layer. And prior to this work, this key parameter, the complex viscoelasticity, had only been fitted to wave data before. So we've developed the first sort of rigorous theory of this in actual bounds. Okay, another large class of problems, again, where we can manipulate the equations to get them into this resolvent structure so that this whole analytic continuation framework applies, is the whole large class of advection diffusion problems, where you have an advection diffusion equation, a divergence-free velocity field, and then you homogenize and you get an effective advection-enhanced diffusivity. And we can develop, and there was some work earlier on based on my work with Papanikolaou by Avelinade and Maida to develop integral representations for this for this effective diffusivity, but then we've taken it much, much further in the last several years. And this applies to lots of problems, such as heat transport in sea ice with convection, ice flows and winds and currents, and so on. Here's just some photos of mine from Antarctica showing some of our beet juice, where we pour beet juice and other kinds of tracers, so you can see the patterns of fluid flow that you'll see in these advection diffusion problems. And then one of the things that we've really done here is to develop the first rigorous theory, or rigorous bounds, on the thermal conductivity of sea ice and other systems as well, but in the presence of model fluid flows. One of the areas that perhaps is most important from a climatological perspective, as well as just fascinating pictures and so on, is these melt ponds. Again, we're still in the mesoscale. And so these melt ponds are very important. If you do not include them in long-term climate simulations, you will not get accurate rates of melting. You really need to incorporate these things into climate models. And so, but I looked at these pictures and I thought, wow, those look very fractally like. You know, there was a lot of detailed numerical modeling of trying to understand the evolution of melt ponds, but we wanted to step back and ask, well, are there universal features of the evolution that are similar to phase transitions in statistical physics? And indeed, we found something fascinating, that the fractal dimension of these ponds increases and goes through a dramatic transition around a area of central critical transition regime of about 100 square meters for the ponds. And so we tried to develop all kinds of models that explain this transition in the fractal geometry. One is we have a random surface and look at the level surfaces, and we're able to then really reproduce this behavior and then study the details by looking at the statistics of the random surface. And then the model that I think we're most excited about is an easing model, where we've adapted a 100-year-old model that describe how materials gain and lose magnetism, and adapt that to explain melt ponds. So the classic easing model, as I say, a 2D lattice, spin up or spin down at each lattice site. And this is a cartoon of the energy, how they interact with an applied magnetic field, and how they interact with their nearest neighbors. And then to lower energy, the spins like to be aligned with each other. They form clumps, ponds. And so here's what they look like in the easing model. And then I just recognized that, gee, the basic physics of spins lining up is very similar to meltwater wanting to clump together to minimize gravitational energy. And so here's magnetic domains in cobalt, here's melt ponds. Here's magnetic domains in cobalt, iron, boron, here are melt ponds. So we adapted the easing model instead of spin up, spin down to be water and ice. And
Professor Golden, I'm terribly sorry, but you have 4 minutes left. And
perfect. Thank you.
We'll need to pose some questions.
Okay, I'm almost finished here. And so anyway, our theory really works. Here's these melt ponds, the real melt ponds, and here's, say, our easing model. We also can then predict the fractal behavior and so on. And then on the macro scale, so we've looked at flow models for anomalous diffusion, where we see subdiffusive, superdiffusive, and diffusive behavior of ice flows bouncing around. So we have a model of that. And then finally, we're interested in, say, this marginal ice zone. And this is on the scale of the entire Arctic, Ocean, where we're interested in the region defined by that goes between less than 80% and greater than 15% of sea ice concentration. And my colleague, Port Strong, has developed a brilliant method based on trying to measure the thickness of the cerebral cortex of a rat brain to assume a very simplified and overly simplified Laplace equation solution, and then to be able to generate go around the whole marginal ice zone and get a quantitative measure for the width, which they then found has widened dramatically as our climate has warmed. And then we're able to use this same technology, I'm sorry, this is a mistake there, to be filled in, to actually fill in this polar data gap with this very simple solution, but we learn a stochastic term there. So I'll skip the conclusions and just thank all of all these wonderful graduate students and postdocs and undergrads and even high school students who have worked with us here. And then you can read a lot about this. We had a cover article in the Notices of the American Mathematical Society back in November that you might find interesting. And then finally, thanks to our funding agencies. So sorry I went a minute over, but I guess I can answer a couple questions if there are.
Yeah, Professor Golden, thank you very much for the wonderful presentation. It's exciting. And please accept my apologies on behalf of the organizing committee for those who are offline listening to the presentation and missed the beginning due to technical problems. At least the recording will be available on the website of the conference later. So we have time for just 2 brief questions.
We have a question.
Yeah, sure.
Okay, thank you very much for the presentation, but I cannot see now the author. I can see Katya only, but nevertheless, so I enjoyed very much the presentation, and I think that the part which I missed was even more enjoyable than the part which I listened to. I was able. Nevertheless, I got some just question relevant maybe to terminology, because you used a term permittivity for the ice. And so permittivity, was it dielectric permittivity? Something relevant to just conductivity? Or was it permeability in terms of seepage flows in ice of some other medium, water penetrating? What was it, the term, what was denoted by this term? Thank you.
So, thank you. Actually, it's both. I mean, the first part of it was on the fluid permeability of sea ice, which defined through Darcy's law. And the underlying physics is similar, but it's a little bit different than the electrical properties. And so then and we use different methods then for this other part, where then I was discussing the complex permittivity, or the dielectric constant of sea ice, and how it responds to electromagnetic waves, then ultimately for applications to remote sensing questions. But they're all related, of course. They're all related.
Oh, I see. But in my opinion, these are absolutely different notation.
Yes, of course they are. And we use very different mathematical methods for each one.
Permittivity is the function of the pore volume content. And you showed their formula, chi0, K is equal K0, and in brackets, phi minus some value in some power. So this is
phi was the porosity. Phi was the volume fraction.
Porosity, yes, porosity.
The porosity.
This is relevant to permittivity, while permeability is never determined by porosity. Permeability is determined by characteristic size of the pores. For one and the same porosity, for example, if one has the glass, just the spheres of definite diameter, then the pack of spheres has the same porosity. But depending on the size, permeability can increase on decreasing size, can increase several orders of magnitude.
Exactly, and that's the constant.
Permeability will be constant. So
exactly.
From this point of view, it seems okay.
That's exactly right. So there's a constant in front in the formula that I showed for the permeability. That K0 is actually 3 times 10 to the minus 8 meters. It's set by the length scale of the pores, exactly as you're suggesting. But you do not have the same kind of length scale at all. It's all in the electrical problem. You only have the permittivity of the objects as well as their geometry. You're absolutely right, but that's all taken into account in these 2 different theories.
Okay, thank you. Thank you very much.
Sure.
Okay, one more short questions. Otherwise, those who are offline would miss the start of the welcome party in the end. Do we have any question maybe from online listeners?
Offline listeners don't have any questions.
Okay. Once again, Professor Golan, thank you very much for the exquisite presentation.